In this lesson, we're going to talk about piecewise defined functions. And before we really get into piecewise defined functions, let's talk about how we go about graphing on a restricted domain. Because if you can grasp this concept pretty well, then you can get piecewise defined functions pretty easily after that. So for instance, if I want to graph the function y equals 2 on the domain -3 to positive infinity. So the domain -3 to positive infinity, this is on the x-axis. So that restriction means my x-axis is restricted from -3 to positive infinity. So normally, the graph of y equals 2 would just be a horizontal line. Oops, I meant to do that in blue. At positive 2. The problem is I'm restricted to the domain -3 to positive infinity. So what I need to do is restrict my function to that particular domain. So the graph of y equals 2 on the domain -3 to positive infinity, that's what that looks like. Simple enough, right? Another example, let's look at y equals 0 on the interval from -1 to 4. So it's -1 inclusive to positive 4 exclusive. So I've got closed circle, open circle, respectively. That's the domain I'm restricted to. Now normally my graph would be the entire x-axis, but if I'm restricted to this domain, my graph is actually, starting here, going over to here, open circle. Another example, y equals 1/2 x plus 1 on the domain from -2 to positive infinity. So even though I'm working with a bit more complex function here, I have an oblique line rather than a horizontal line, the concept is the same. My domain is restricted from -2 up to positive infinity. Now if I had graphed this function normally, positive 1 is my y-intercept, and my slope is 1/2. So if I go up 1 over 2, up 1 over 2, and down 1 back 2, down 1 back 2, then this would have been my line originally. The only difference is the line is restricted to just the domain from -2 to positive infinity. So all of these points on the line don't exist. Let me get back this part. And actually my line just starts right here at this open circle. So that's that particular line graphed on that domain. Okay, let's say I have y equals -3/2 x plus 2 on the interval from -2 to positive 4, and the 2 is excluded, but the 4 is included. All right, this time I'm not going to draw the entire line, I'm just going to draw it on this particular interval. So positive 2 is my y-intercept. My slope is -3/2. So if I go down 1, 2, 3, and over 2, there's my next point. Then if I go down 1, 2, 3, and over 2, there's my next point. And I can stop there because that's the end of my interval. And if I go up 3 and back 2, there's another point. But this point is actually going to be an open circle because if you'll notice, I'm not including the -2 for the x. So now I just draw my line in according to that domain restriction. And a couple more quick examples here. This time I'm restricting myself from -infinity to positive 2. The 2 is included. All right, now y equals 1/2 x minus 4. So down 4, 1, 2, 3, 4. There's the point right there. My slope is 1/2, so I would go up 1 over 2, and that gives me another point on my line. Or I could go down 1 and back 2 and get myself another point on the line. So this is definitely a closed circle, and I'll just put an arrow there because it's continuing on to infinity that direction. And one last example here. This time I'm restricting myself from -4 exclusive to +2 exclusive. And I have the line y equals -x minus 1. So there's -1. The slope is -1. I'll go down 1 over 1, down 1 over 1, or up 1, back 1, and so forth. Okay, I have open circles at the start and end of my interval, and connect my points in between. And that's all there is to drawing a graph on a restricted domain. And if you can handle that, you can definitely handle anything that we're doing with piecewise defined functions. So let's look at an example of what one is. So a piecewise defined function is a function that's defined by multiple functions, each on a non-overlapping restricted domain. So for example, this right here is what a general piecewise defined function looks like. Now, sometimes I've seen textbooks put commas in between the functions themselves and the domains. I've seen textbooks, insert the word if, for each one of these. Those are, dependent on, different authors. But this is the basics of it. So I have two functions. So the first function is the x minus 5, and the second function is the 3. They're connected together by this brace here that tells me that they're being joined into one function. And the first function is only defined on the domain where x is less than -2, less than or equal to -2. And the second function is only defined on the interval where x is greater than -2. And notice, if I drew a number line, that these are non-overlapping domains. So here's -2. The first function, which I'll draw in green, is defined where x is less than or equal to -2. The second function, which I'll draw in blue, is defined where x is greater than 2. Because one side is an open circle and the other one's a closed circle, there is in fact no overlap here. And so that's really important that these are each on a non-overlapping domains, because if they were overlapping, they would not be functions anymore. Okay, let's look at how we go about evaluating piecewise defined functions. So here's a piecewise defined function, and let's say that I want to evaluate f of -3. Well, if you want to get this wrong, take the -3, plug it into each one of the functions, get 2 answers, and write that down. Guaranteed to get the problem wrong. If you want to get it correct, here's what you do. So x in this case is -3. -3, you come over here to these bounds and you see which of these intervals -3 is on. So the first interval where x is less than or equal to -1. So if you think of a number line, here's -1, -2, -3. So -3 is less than or equal to -1. So that means I'm going to use this top function here. So I would be evaluating 2 times -3 minus 1, which would be -6 minus 1, or -7. I just get one answer in this problem. Okay, next example, f of -1. Well, because this is less than or equal to -1, that means I'm on this domain still, So I'm still going to be evaluating using this top function. So I would evaluate 2 times negative 1 minus 1, which would be negative 2 minus 1, or negative 3. Next up, f of 0. Well, 0 is greater than negative 1. So that means I would be using this function to evaluate this one. So I could be doing, say, 0 squared plus 3, which results in just 3. And lastly, f of positive 2. Well, positive 2 is greater than 1, so that means I'm using this function again. So it would be 2 squared plus 3, which is 4 plus 3, or 7. So that's how we evaluate piecewise defined functions, but a lot of the time what we're wanting to do is actually to graph these things. So we kind of pull together what we just did a minute ago with graphing on a restricted domain, but we just do it for multiple functions. So for instance, this first domain I'm going to color in green, so where x is less than or equal to negative 2. So x is less than or equal to negative 2 right here. Now I'm going to draw this function right here on that restricted domain. So negative 2 is a constant, and it's just going to be a horizontal line at negative 2. And I use my open circle because I'm so sorry. I would be using a closed circle because it's less than or equal to negative 2. You probably noticed that, and we're asking that question. Now, that's what that's going to look like on that domain. So I'm going to get rid of this stuff, and I'm going to go down to my next function. So now I'm looking at the domain where x is greater than negative 2. So x is greater than negative 2 is this domain over here. Now I'm going to graph the function positive 3 on that domain. So starting here and going this direction. So now this is my piecewise defined graph. So if you'll notice, there's kind of like this breakpoint right here at x equals negative 2. So one way to think of this is, identify where that point is, draw what's happening with your functions up to that point, and skip over it from there. All right, let's look at another example. So this one's another relatively simple example, but I'm not going to draw my domains first. I'm just going to draw this, knowing that like x equals 2 is kind of this breakpoint. And the first part of my function is defined for positive 3. So I have a horizontal line, positive 3, up to positive 2, but not including. And then starting from positive 2, I now have a horizontal line at 1, which looks like that. So especially if you just have constant functions, these are generally pretty easy to draw. Okay, another example here. A little bit more complex, but we still have a constant function and a linear function. Now there's no reason you can't start with the constant function. So if I'm trying to draw this, I know that I have this kind of division at x equals 0. So the function positive 2 would look like this, just a horizontal line at positive 2 starting from x equals 0 going forward. Now the other part where x is less than 0, okay, so that's that domain there. The function itself, I would just draw a regular line. So at x equals 0, this is going to be at negative 3, but it's going to be an open circle. My slope is negative 2, I can't go down 2 and over 1 because that's going to take me outside of my domain, but I could go, say, up 2 and back 1, up 2 and back 1, and so forth, until I feel comfortable with the line that I've drawn. And then I'm going to take away this domain part here because that's not actually part of the graph. And that's my answer. And one more, a little bit like that. We have a linear and a constant, but everything's kind of changing at x equals 2. That's kind of the break point here. So when x is greater than 2, my function is constant at -3. So I'm just going to draw that in really quick. That's easy. Now, the other half, where x is less than 2, or less than or equal to 2, I'm sorry, would be this direction. That's that domain. And I want to draw the function -2x plus 1 on that domain. So y-intercept is +1. If I go down 2 and over 1, there's another point. Down 2 and over 1, there's another point. Or up 2 and back 1. Whoops. And up 2 and back 1. There's my line. Now, here's the thing about this. If you'll notice, this point here ends up being in the exact same place as the open circle that I had before. That's actually perfectly okay and can happen sometimes. And I just fill it in with a closed circle. And what ends up happening here is I end up with what's called a continuous line on that part. So when we talk about continuity later on in the class, continuity generally means that you can draw a graph without lifting your pencil, for a very simple definition, that is. And so when you have piecewise defined functions, such as, in C here, there's no way I could draw this graph here because of this giant jump without lifting my pencil, so this would be a discontinuity at this point. But right here, this graph would be continuous on D because it connects at this value. So when we talk about continuity later on in the class, that sort of thing will be useful to know. All right, I have some more examples here because this is generally a challenging subject for students, so let's do as many as we can. So now I have two linear functions. The first one is defined when x is less than or equal to -2. So here's -2, and that's less than or equal to it. And then the other one is defined when it's greater than 2, greater than -2. Now, the problem with graphing as I do normally is that I usually start with the y-intercept when graphing a line, but this y-intercept, or actually it was at -1, but that y-intercept isn't on this domain, so it's not really any helpful to use there. But you can always use a point plotting method, and I actually find a point plotting method to be somewhat easier when it comes to graphing lines with piecewise defined functions. So here's what I mean. So what I'm going to do is start with this breakpoint as one of my points. So if I plug that into my function, then the opposite of -2 minus 1 would be 2 minus 1, which is +1. So at -2, my graph here is at +1. So that's a point on my graph. And from there, I can just use the slope. So my slope is -1, so right along this line right here is what I'm looking for. On the other half, where x is greater than 2, again, or greater than -2, again, I'm going to plug in the -2. So it would be -2 plus 2. I'm just plugging it into this function though. But notice, well, actually, that evaluates to 0. But notice, however, that this isn't contained on that domain. And that's actually okay. This is just telling me the location of that open circle. So I have an open circle right here at 0, and then my slope is 1. So it would look like, the rest of my line would look like that. So that's generally how I go about these linear ones. So let's try that again here. So I'm going to plug this point 1 into both functions. So at x equals 1, 2 times 1 plus 1 equals 3, and negative 1 plus 2 equals 1. All right, so at 1, so positive 1 on my x-axis, I'm going to have an open circle at 3 and a closed circle at 1. So that gives me 2 points to start with, and from there I'm just going to use the slopes to come up with the rest of the line. So for when x is less than 1, my slope is positive 2. So if I go, say I have to go down 2 and back 1, down 2, back 1, and so forth to draw the rest of that line. And when x is greater than or equal to 1, my slope is negative 1. So that's going to look like, you know, down 1 over 1, down 1 over 1, and so forth. And so there's my graph there. If you have functions that are nonlinear, then that type of method may not exactly work for you. So point plotting might be the best thing to do. Like for example here, I've got a quadratic. So what I'm going to do is exactly what I did in the last example to start off. I'm going to take positive 1, plug it into each of these functions, and just see where the open circle and the closed circle at positive 1 are going to exist. So at x equals 1, 1 minus 2 will give me negative 1. So at negative 1, I'm going to have a closed circle. There we are. And at the other, negative 1 squared plus 2 would be positive 1. So that's going to be an open circle on that interval. So I'm going to have an open circle there. Now, my linear function, x minus 2, the slope is 1, so I can just use that slope to come up with the rest of these points, just like I was doing in the past. But the other function, the quadratic, I'm not quite so sure exactly how that's going to work out in terms of slope. This point might be a vertex, it might not. It's really kind of hard to tell. Best thing to do, just plug in another point that's on your domain. So where x is greater than 1, I could just plug in x equals 2 into that thing. So it'd be negative 2 squared plus 2, which would be negative 4 plus 2, or negative 2. So at positive 2 on the x, I'm at negative 2 on the y. So my parabola just kind of looks like that, I guess. And that's pretty decent sketch here. All right, one last one. I've got 3 functions, and no different really. You're going to do the process that I gave you basically 2 different times. So you're going to start off with the first boundary point, which is negative 2. If you plug negative 2 into this function, obviously it's just 3. There's no x values to substitute in. No matter what you put in, you get positive 3 back out. So at negative 2, I'm at positive 3, but that's going to be an open circle. And because it's a constant function, I'll go ahead and graph that. All right, but if I put negative 2 into this function, it would be negative 2 plus 1, which is negative 1. So at negative 2 on the x, I'm at negative 1 on the y. Now, the next thing that I'm going to do is concentrate on the other border point, which is 1. And I'm going to plug 1 into this function and 1 into this function. And so it would be 1 plus 1, which is 2. So positive 1, 2. That's going to be an open circle. And I'm going to go ahead and just connect those because, you know, 2 points is fine to draw a line. That's all you need. And then if I plug 1 into the other function, it's going to be negative 1 plus 3, which is positive 2. So 1 and 2, looks like these actually meet up together. And then the slope is negative 1. And there we have it. Now the last part of this video, I want to go into the homework assignment and show you how to go about answering the last couple of questions in the homework where you're asked to show your work on a piecewise defined function. You see, most of the homework is basically going to give you a piecewise defined function and 4 different graphs, A, B, C, D, and you choose the correct graph. Which, unfortunately, when you come to take the final exam, you're going to be required to actually draw one. So in order to make this happen, I'm creating some questions in the homework where you actually have to show your work, which should be relatively easy for you to do, and I've got a couple of options to show you here. So when you get to that question in the homework, you'll see the button that says to show work. So if you click on that, one thing that you can do is, you know, if you want, you can use your mouse and just draw in here. And it's not going to look very good, especially if you're using your mouse. I mean, this actually isn't too bad, but you know, I'm using a smart board, so it's a little bit easier for me. So you could literally just draw in, you know, whatever your piecewise defined function should look like, and you know, that would be great. Now, the issue with that is, again, if you're using a mouse, it's not really going to look very good at all. So let me just delete this work and show you another option. So another option is to actually just draw it on paper, take a picture of it with your phone, or if you happen to have a scanner, you can just scan it in. But you need to scan it in as like a JPEG or PNG bitmap, not a PDF. So you want to scan it in as a picture file. If you just take a photo of it with your phone, it's going to probably be a JPEG. And you can hit this button here, which allows you to insert an image. So you just have to basically like take a picture on your phone, email it to yourself so you can download that picture on your computer, and then you can upload it here. So let me find that file and I'll upload it. Okay, there's the one I did earlier today, and it will just insert that picture into your work here. Then hit save, and you'll see that the show work border has turned to green, so you've submitted your work, and now it'll actually wait for me to go and look at it and grade it. So the only thing that's kind of unfortunate in this process is that you won't get the grades for these immediately like you do with the rest of your work, but I think that having the experience of drawing these is going to be, you know, better served this way in preparing you for your final exam, because there will be one where you're required to draw. And also on the unit test as well. All right. And one last thing I should say about that is when you submit the work for the show work problem, you should send me an email and let me know that you're ready for me to grade it so that I get in there and grade it for you.